Thank you, Ryan. I'm Aman Sheikh. I'm from AT&T. Now, if you see me a little bit nervous, the reason is because I saw AT&T as number 3 in that list of providers that are at risk. So it has nothing to do with this presentation. In any case, I'm going to talk about virtualized PE for layer 3 VPN service using open source software. Let me get started by stating our objective. Our objective was to demonstrate feasibility of creating a layer 3 VPN VPE using open source software. And feasibility is a key word here. We are primarily focused on showing that one can create a VPE using open source software for layer 3 VPNs. There are other aspects of creating a VPE or using a VPE, such as performance, robustness, advanced features, and we are not focusing on those in this particular talk. So then the next question is, why the hell do we want to create a VPE? Our first motivation was to create a use case for AT&T's DNOS, which is the disaggregated network operating system. AT&T has published a white paper related to DNOS, and release is imminent at the end of the year. So that was our first motivation. The other motivation for actually having a layer 3 VPN VPE as use case is based on 3 keywords in there: L3 VPN, VPE, and open source software. L3 VPN is a service I'm sure all of you are probably familiar with. This is a service that service providers like AT&T can provide on a shared backbone, where they can create an illusion of virtual private network for lots of different customers. And I'm sure if you are an enterprise or if you are any kind of business, you probably connect to a service provider and access this service in order to connect your different sites, which might be geographically distributed. So this is a widely used service. Why VPE? Well, it turns out that VPE is a key VNF for this service. This is the network function that sits at the edge of the service provider network and connects to the customers. And when the traffic comes from the customer or goes out to the customer, this VNF is what acts as an entry point and an exit point for the traffic. And finally, open source software. And I don't think I need to say much about that. The open source software allows increased agility in rolling out new features, programmability, etc. And so these were our reasons for trying out this experiment. And as we expected, we faced numerous challenges. The open source software that we decided to use didn't run as is. It didn't just use out of the box from day one. We had to make some enhancements which were related to functionality, as well as putting these software pieces together. So there were enhancements that we had to do related to integration as well. And as we go along, there will be details about these things in my presentation. So here are the software components that we used in our open source VPE. For the control plane, we used 2 softwares. One is called FRR, free range routing. And in particular, we used OSPF, LDP, and Zebra components from FRR. And then the second software that we used is called GoBGP. And as the name implies, we use GoBGP for its BGP functionality. As for data plane, we chose AT&T Viata's DPDK based data plane. And together with the control plane that I just described, that's what forms the DNOS use case VPE. But in addition to AT&T's data plane, we also verified feasibility with just pure Linux data plane. So essentially packet forwarding using Linux kernel. And we also used VPP data plane. In particular, it's release 1801, plus some modifications to the router plugin, which allows VPP to communicate with the control plane. This is a picture of what the VPE looks like. Both the control plane and Viata DPDK data plane actually run in Linux user plane as Linux user plane processes. In particular, in control plane, we have GoBGP, FRR OSPF, and FRR LDP running as separate processes. All these processes learn routes from their neighbors, they select their best routes, and then they install these routes down into FRR Zebra, which runs as another process. FRR Zebra in this particular case communicates with AT&T via a route broker, which is a scalable and reliable platform for RIB management. And the route broker in turn programs the FIB for the Viata's data plane. The routes can also be pushed to Linux kernel forwarding table. So in fact, when we replace the Viata's DPDK data plane with pure Linux, the route broker and the Viata FIB go away, and the FRR Zebra process directly communicates or installs route into Linux forwarding table. When we use VPP, what happens is that VPP again runs as a user plane data process, just like Viata DPDK data plane, but instead of communicating with route broker, it syncs its routes with the Linux kernel forwarding table. Okay? So this is what the picture looks like of the test bed that we used for verifying feasibility. In the middle is a service provider. I bet this is the smallest service provider that any of you have seen in your life. It has only 3 routers, 2 PEs which are interconnected by a core router. And the core router doubles up as the VPN v4 route reflector as well. Inside the core we use OSPF and LDP for connectivity between VPEs. Now this service provider in this testbed provides connectivity to 2 customers, blue and red, and each customer has 2 sites, on the west and on the east. So you can see that VPE west is connected to west offices of both the customers, and similarly VPE east is connected to 2 offices, offices of the 2 customers. And with this setup, in order to verify feasibility, what we do is we run video stream for each customer from its video server on the right, all the way down to its video client on the left. And similarly, we do the same thing for the red customer. So these video streams are run concurrently when we do our verification. Not only that, the other thing that I would like to point out is that both the video servers have the same IP address, and similarly, both the clients also have the same IP address. And this is to show that when you use VPN, customers are free to choose their IP address assignments. And in this particular case, they have this situation where they are using the same IP address, and even with that, VPE is able to keep the traffic segregated across the customers. So despite using same IP addresses and running the video streams concurrently, the VPE is able to do what is expected of it in terms of providing L3 VPN service. Now I wish I could show you the videos, but unfortunately I cannot. So what I did is the next best thing, which is to capture packets when we did one of our feasibility and or rather when we did one of our verification testing. And this is a snapshot of packets that were flowing through the core router, which is sitting in the middle. And in particular, we captured packets that were coming from VPE East into the core router. So this is the interface that's facing VPE East on the core router. And over here, what I've done is I have highlighted 4 packets. The first one is going from red server to the red client. And the thing that you need to note here is, and I don't know how well it is visible, but you will see that this is a packet that has 2 MPLS labels. The outermost label is for the loopback of VPE West, which is the egress for traffic going to the client. And the inner label 145 corresponds to the red verb on VPE West. The next packet, the second packet, is going in the other direction. So this is the packet that's going from client to the server. And this packet, if you note, only has a single MPLS label. And this label corresponds to the red verb. Now the reason that this packet has only a single label is because it is captured at the interface towards VPE East. So the core router does what is known as penultimate hop popping, which is removing the outer label for VPE East before the packet is sent out. And that's the reason why you're seeing only a single label in this particular case. Similarly, the third packet is going from blue client to blue server, and again you see a single label which is 144, which corresponds to the blue verf on VPE East. And the last packet is again going in the other direction from blue server to blue client, and you can see two MPLS labels, the outermost being the label for VPE West, and the innermost label is for the blue verf. Okay. So next what I'm going to do is go through the configuration details, in particular how we configured our testbed to verify feasibility. And I have divided the configuration into two parts. The first part is about establishing LSP or label switch connectivity between PEs within the service provider network. And then the second part deals with enabling L3 VPN service on top of the LSPs established within the service provider network. Before I go into the details of configurations, let me mention that we use two loopback addresses on every box running in the service provider network. In particular, the first loopback, which I call loopback 1, is used for IP traffic, especially the control plane traffic related to OSPF, LDP, and BGP. The second loopback is used for MPLS traffic, and so all the customer traffic for the VPN customers uses loopback 2 or is bound to loopback 2 of the boxes in service provider network. So this first slide shows how you enable MPLS forwarding on Linux itself. So these are the set of commands that we need to run on every box to enable MPLS forwarding. Here I am showing them for VPE East, but similar commands were run on the other two boxes. So the first command is to enable IPv4 forwarding. The second command is to enable MPLS modules. The third command actually enables MPLS forwarding on the particular interface. In this case, the interface facing the core router. And the last command is to allocate space for the MPLS label table. So once you run these four set of commands, the box can act as an MPLS forwarder. But of course, you need to program the box. And in order to do that, as I mentioned, we run FRR, OSPF, and LDP processes on all the three boxes within the service provider network. On the left, you see OSPF configuration for VPE East. On the right, you see configuration for LDP on VPE East, and it's fairly standard. If you have done OSPF and LDP configuration, this will look very familiar. You configure router ID for OSPF, add both the loopbacks to the OSPF, and you enable adjacency to the core router, in this case, within the OSPF configuration. On the LDP, again, you see router ID configuration, and then you specify the interface over which you want to enable neighbor discovery. So in case of LDP, instead of specifying neighbor explicitly, we ask LDP daemon to discover neighbor automatically, and that's what the configuration over here shows you. So once this configuration is in place and once OSPF and LDP processes are running along with Zebra, the service provider network has label switch paths enabled within itself. So now you can ping from one PE to another, you can reach them, there is connectivity between these PEs. So now we are going to move on to enabling layer 3 VPN service. The first thing we are going to do is enable VRFs or VRFs on the Linux box at the Linux level. So what we are doing, again, this is on VPE East, and similar things were done on VPE West. So on VPE East, the first set of commands create blue VRF as a link or as a device and brings it up. The next command, the fourth command on the screen, adds the interface facing the VCE to the VRF. So in this particular case, this is the interface facing VCE blue East, and that's added to VRF blue. And the last set of commands are interesting. This allows BGP process running on VPE East to listen on port 179 on VRF bound interfaces. Without running this command, what happens is that the BGP process listens on port 179 as it usually does, but it only listens on those interfaces which are bound to the default routing table or default forwarding table. In order to make BGP process listen to port 179 on WRF bound interface, we have to run these two syscontrol commands on Linux CLI. This is the BGP configuration on VCE. For VCEs, we used FRR BGP daemon, and you can see the configuration over here. The second line, which I have highlighted in the configuration, allows configuration of the session to PE's loopback as opposed to the interface facing the VCE. The rest of the configuration again is fairly straightforward. You have router ID. We then enable or we add those networks related to video server to BGP process. And finally, the two set of commands enable peering session with VPE East. Next is the Go BGP configuration on VPE East. Three key points here. The first key point is that in order to use next hop self, which is basically assigning the next hop as the loopback of its own interface, we had to use an export policy. So as routes come in and go into the service provider network, this policy attaches the loopback to of VPE East to the routes as next hop. The second box here shows how we communicate with Linux kernel and via data plane via FRR Zebra. And the last set of commands show how iBGP session is established with the route reflector. This slide has details of how the next self policy works. So at the top is the set of routers for which we want to apply the export policy. And in this particular case, the route reflectors is the only router that we care about in our small ISP over here. And then the next set of commands show that when routes go to the core router, you attach loopback 2 of this PE as the next hop before sending the routes out. So this is how the next hop self policy is realized in Go BGP configuration. The last bit is about configuring WRF and eBGP neighbor. Now ideally I would have liked to configure them using Go BGP configuration file, but the Go BGP version that we were using didn't allow WRF configuration. So we had to rely on Go BGP CLI to do the WRF configuration. And you can see that the first command adds blue WRF along with its route distinguisher and route target. And the next command adds the neighbor session and attaches it to the blue WRF. This is Go BGP configuration for route reflector. Again on route reflector, which is co-located with the core router, we use Go BGP as our BGP process. The configuration is fairly standard. You configure AS number, router ID, etc. And then there is the session, iBGP session for VPE East. And similarly, there is another session configured for IPE West. One thing I'd like to point out is that there is no communication happening with FRR Zebra here, because the only routes that this route reflector learns and distributes are VPN v4 routes, and these routes do not need to be pushed down to the forwarding table, because core router only switches packets based on MPLS labels and not VPN v4 prefixes. So that was all about configuration. Next, I'm going to talk a little bit about implementation. And in particular, I would like to talk about L3 VPN support in Go BGP. As far as implementation goes, there are two key aspects. Number one is what I call key building blocks. This is essentially the machinery that you require to be able to do layer 3 VPN in Go BGP. So things like internet routing with BGP is a necessity. The other aspect that we require is able to partition routing table into a global table and WRF specific tables. We need support for VPN v4 and v6 address families like IP prefixes, route distinguishers, and MPLS labels. And finally, we require support for route targets, which allows us to associate routes with VRFs. Now, as far as these building blocks are concerned, GoBGP had everything that we wanted, so we could use them straight away out of the box. But then there is the second key aspect, which I call interaction with outside world. So things like configuring VRFs. So this is where a user configures WRFs and associates an eBGP session with GoBGP. Then the second aspect is about handling routes received from a CE, similarly routes received from route reflector or remote PEs, and finally communication with Zebra. So these four aspects which are about interacting with outside world, this is where there were some pieces that were missing in GoBGP, and we had to do some enhancements to the code to make them work. Okay. So let me go through the details of those enhancements. This is the case where GoBGP handles a route received from an adjacent CE. The CE over here is on the left side, VPE is in the center, and the route reflector is on the right side. So let's see what happens when VCE sends a route. Note that this route for prefix P is a pure IPv4 route, and this is what customers usually send to service providers. Now let's see what happens with this route. Let's say that this route is installed in the blue WRF as it should, because the session is associated with the blue WRF. And then when BGP runs its decision process and installs this route into FRR Zebra and into the FIB, this was the place where things didn't work correctly with GoBGP. And this is where we had to do some enhancements to GoBGP to make this work. Okay. Now the route is also imported into the global table, and this is the place where the IP prefix is turned into a VPN v4 prefix by attaching a blue specific route distinguisher and blue MPLS label. This part worked fine, except that we had to do an enhancement for attaching MPLS label with the route. And then finally, this route is sent out to the route reflector for distribution to other PEs. And in our case, it will be the other PE, the second PE. The communication part or the sending of the route worked fine, and we didn't have to make any modifications to GoBGP in this particular case. So as far as handling routes received from an adjacent CE is concerned, we had to make two modifications. One was how the route is installed into FRR Zebra, and the other is how MPLS label is attached to the route. Or in particular, we had to make sure that the correct label is attached to the route before it is imported into global table. Now on this slide, I'm showing how GoBGP handles route when it comes from route reflector. So these are the routes that are coming from the other PEs. So let's see what happens when a route reflector sends a route. Note that the route is a VPN v4 route, so it has route distinguisher and MPLS label attached to it. This route is first put into global routing table by GoBGP. Everything good so far. Now what GoBGP does is something curious. It actually pushes this route down to the Zebra daemon, and then Zebra will install the VPN v4 route into the forwarding table. This is not a deal breaker, but it's not something that is required. And in particular, if there are 100 or millions of routes, this can actually lead to scalability concerns. So what we did is we disabled the part where GoBGP actually pushes the route down to FRR Zebra so that it doesn't go down into the forwarding table. The route is then imported into blue WRF, and when it is imported, the route distinguisher is removed and the route essentially becomes an MPLS labeled IPv4 route. So the blue label is still associated with the route. And then eventually this route, after it goes through the route selection process, needs to be installed into the RIB and down into the forwarding table. And again, here we had to make some enhancement to make sure that the route was installed into the word forwarding table with correct label. So as far as, let me finish this. And so after that, the route is sent as a pure IPv4 route to the VCE. So as far as this scenario is concerned, where the route comes from route reflector, again we had to do two modifications, and both had to do with how routes are communicated down to the Zebra daemon. So this brings me to my last slide. So in summary, what we demonstrated was that we could indeed create a layer 3 VPN VPE using open source software. In particular, we used two softwares for control plane, GoBGP and FRR. And in case of FRR, we ended up using OSPF, LDP, and Zebra daemons of FRR. For data plane, we use three distinct data planes. One is AT&T's Viata data plane, which is DPDK based, but we also verified feasibility with VPP and pure Linux forwarding planes. This required us to make enhancements to GoBGP, so things didn't work as is straight out of the box. In particular, we had to make modifications which required which dealt with how routes are installed into forwarding table, how MPLS labels are assigned to VP and V4 routes, etc. And if you are interested in more details, or if you are interested in the modified code, it's available on GitHub. There is a URL there. And there is also a URL for DNOS, or Disaggregated Network Operating System, if you are interested in learning more about it. And with that, in fact, I finished fairly early, so there is ample time for questions. Thank you. Any questions?
Michael Smatrik, yes. I think I completely missed it. I like the idea of using GoBGP, but I'm not sure why you didn't just use the FRR BGP daemon instead brought in GoBGP. Was it scalability, or was it something else?
No, that's a good question. So when we started this project, it was last year, sometime around this time last year, and at that time FRR did not have support for VP and V4 at all. And that was the reason why we went ahead with GoBGP. Now what has happened is that in the meantime, I think sometime this year, FRR has started adding support for VP and V4, and we in fact tried it out in our testbed, but so the VP and V4 part works fine. The place where we had some trouble was again the policy for setting the next hop to its own loopback address. But in near future, we are again going to try out FRR.
Thanks.
Any other questions?
And requesting exam solutions. From your presentations, I saw what in the initial state, the daemon that was expected to perform MPLS function was able to do VRFs, but was not able to do basic label operations like exporting labeled routes to proper tables and exchange routes with route reflector, and also install route into proper routing table. Mm-hmm. So it looks like it didn't have capability to work with MPLS at all, but only like VRF Lite support. Is it correct, or is it something?
Yeah, so I think you are referring to this slide?
Yes.
Yeah, so you're mostly correct. What happened is that GoBGP had MPLS support, but what it was not doing was it wasn't attaching MPLS labels to the routes. So when the routes went out to route reflector, they went out as VP and V4 routes, but the label was always initialized to 0.
Yeah. But
Okay.
So initially with daemon is designed to operate only in VRF Lite mode, it turns out, right?
I suppose, but
Oh.
I'm not 100% sure with VRF Lite whether you need MPLS labels or not.
Yeah.
But in this particular case, we needed MPLS labels.
Yeah, yeah.
And so the routes had a place for MPLS label, but they were always initialized to 0. So in fact, I can show you something which is in the backup. Yeah, this slide. So when we configure the VRF, now with the change, what happens is that forget about this part, but once the VRF is configured, GoBGP contacts FRR Zebra and obtains a label and associates it with the with the specific VRF that you are trying to configure. And this is the label then, which is then propagated along with the route to the route reflector. Does that make it clear?
Yeah, I just was wondering how it was expected to operate without this functionality. So
I don't know. So that's where I think, I don't know how many people had actually tried to do VPN, layer 3 VPN with GoBGP. I have no idea. And then when we tried, we ran into some of these problems. In fact, when we tried it first, we could only get basic internet connectivity to work. And there were all these issues which prevented us from doing a full-fledged layer 3 VPN.
So it looks like that you just brought the necessary functionality to this daemon. So
Right.
Thank you.
Yeah, sure. Any other questions? I guess we can then have early lunch. Thank you so much.